Okay.
Thank you, Javier.
All right. Well, thank you for that. Let's start again.
Welcome, EECS 16A. Woo!
Okay, so I recommend going like this. It opens your lungs, brings air into your brain, and just gets you into the mood of to the lecture. So I highly recommend going that. A couple of announcements. So our aim is to educate you. So and it's probably the first time for some of you, it's the first semester at Berkeley. So we're going to try to ease you into taking an exam at Berkeley, and also because we're going to use an online exam, to just be able to practice that. So we're going to have not a big midterm, we're going to call it a quest. And it's a short midterm. It's only about 30 minutes or so. It's going to be on Tuesday, September 14th at 8:30 p.m. It's just going to be half an hour. And they're going to cover all the material, including today. So what I'm going to do today is try to catch up to the material that I wanted to do that. Don't worry too much about it. It's really just to get you into kind of like the mood. But the nice thing about the quest, it's only 5% of your grade. And if, let's say, you do not do well, which you shouldn't not do well, but you should do well, then midterm 1 would pretty much clobber the quest. So we have a nice clobbering policy that if you are tested on a material that you've been tested before and you do better, then you learn the material, so you're just going to get the latest, the best grade out of all. So if midterm 1 is much better than the quest grade, then the quest grade will be replaced by your midterm grade. Okay. Midterm 2 doesn't clobber anything because it's going to be new material, but the final will clobber midterm 1, midterm 2, and the quest. Okay, so our incentive to you is to hedge. That means that you need to do as well as possible on the quest, midterm 1, midterm 2, because the final can be pretty tough. So in that sense, midterm 1, midterm 2, and the quest will give you some hedging, and so some averaging, and some will if you don't do as well as you hoped on the final, so that will help you. But if you do much better on the final than all of these, then you get the score of the final. So pretty much it's just here to help you. Okay, we're here to give you kind of a support, and we really want you though to take it seriously, because it's not every day is your best day. So learning is a process. Anything else?
And knowledge is cumulative. So it might be that you're struggling today, but you learn, you do fine at the end. And that's what we want. We want you to get there. So, but study all the way.
You ask people asking the tips to prepare for the quest. Yeah, just solve problems, and that would be the best. There's not that much material. It's just 3 lectures, right? So how much can we ask? All right. Anything else that we want to announce?
Monday's a holiday, so no lab next week and no lecture on Monday. Or no discussion on Monday, I'm sorry.
No, right. And so one thing I have to say about the discussion. So again, we apologize. We started the semester in the middle of the week. So we only had 1 lecture and then immediately had a discussion. So the discussion yesterday was a little bit ahead of class. I was a little bit slow. Apologize for that. But because Monday doesn't have any discussion, then now we're going to go back. And so we had to manage that somehow without losing too many discussions and exercise. Okay. So, all right, let's move on. We've got a lot of things that I'd like to catch on today. We're going to talk about linear algebra. This class deals and uses a lot of linear algebra. This is, by the way, just a repeat of last week. And we talked about the definition of linear equation last time, in particular, the properties of homogeneity and superposition. What I did not actually mention is that once you have homogeneity, really superposition is the property of both. Both the multiplication of the input results in the multiplication of the output. And then if you put two inputs in, add the two inputs into a system, it's the same as putting one input into the system and measuring its output, putting another input into the system, measuring the output, and adding those together. So addition in the beginning or addition at the end is the same. But you can also combine both of them. So you can also scale one of those inputs and scale one of the other input by another factor. And when you add them both together, then what you'll get again is like putting the first scale input into the first, putting the scale input into the second, and then adding the results together. Okay, so this property is really the superposition. So it adds both the scaling and the addition of those two. And doing that results in the fact that linear set of equations. So we show that taking those properties results in the fact that if you have a linear set of equations, you can represent it as a sum of constant coefficients multiplied by your variables. Constant coefficient multiplied by your variable, sum of all of these. Okay, this is the result of this, and we proved this last time. In particular, we use this property that uses both of these properties, okay, together. Okay, and then we showed this last time, and in particular, sorry about that. In particular, the last step that we did last time was using the property that I showed before over here in order to separate, and then we showed that you can actually represent those coefficients. And I showed this for r equal 2, but it's really trivial to extend that to r equals n. Okay, and one thing that maybe we could ask you is, how to scale that into r equal n. And I actually highly recommend of reading the notes. The notes are a very deep elaboration of what we cover in class. So in class, it's kind of more like an advertisement of what's in the notes. And I highly recommend looking at the notes. It's much more descriptions there, much more examples. And those follow pretty much the material that we cover in class, but a little bit in more depth. So I highly recommend reading those notes. And if you have a chance to read the notes ahead of time, that's even better because you'll be prepared and you'll understand more of what we're talking about in class. But that's up to you. Okay, so we talked about the linear set of equations. So here's the case where you have m linear equation, each one with n variables. So m like Mike with n like November. And so we have a set of m of these, and we have n variables. And this is pretty cumbersome to write. You have to put all those x's and everywhere. So what we introduced last time was the compact representation using what we called an augmented matrix. We didn't really even talk about what matrices are and what their properties and so on and so forth, but pretty much is mapping this equations into some other form that looks, just a set of numbers that represent pretty much the coefficients of these equations. And so pretty much if you, this is the augmented matrix form, where you see the A11 that multiplies x1, we just put it here. And the A12 that multiplies x2, we just put it over here. So this column over here represent the multiplication with x1. This column over here represent multiplication with x2, and this one with xn. And the rest, after the line is what it's equal to. Okay, so pretty simple. It's just a mapping from here to here in a nice way. So it's just a nice, and I called it syntax sugar, right? Because it's sweet, right? Sugar sweet. So now let's go back to tomography, and pretty much we, if you remember, in tomography, and let's go back, we said, oh, if we shine X-ray through here, so X1 plus X2 may equal 4. That's the amount of rotation. If you shine X-ray through here, then X3 plus N. So we can have a set of equations, and this is the set of equations that we had. And now we can write it down into an augmented matrix form. And I did that last time, so I'm just going to show you how you put it together. And again, we just map those coefficients into here and map those coefficients into here and so on and so forth. And this is what we get. And now the question is really, how do you go about and solve it? Okay, that's really the key, because we really want to solve it. So the thing is, this is just four variables. So, probably in middle school, you were able to solve such an equation. Maybe in high school, not a problem, right? Like you can substitute, you can find a solution for that. That's not a hard thing to do. But the problem comes in really because our images in CT are not 2 by 2. They're more like 256 by 256, 512 by 512, 1024 by 1024. In that sense, we'll have 1024 square number of equations, at least. Well, that's a lot of equations. So it's going to look more something like this. And yes, Anna?
Can you go back a slide, please?
Yes.
And can you say a few words why we have the square root of 2 in this matrix?
Oh, yeah. Somebody asked why we have a square root of 2. Well, again, this is the model, right? Like we said, we're modeling things. So we said, oh, we're going to shine X-ray from here to here, right? And so, how much path we go through, like how much attenuation depends on the distance. And if you actually look at a diagonal of a square matrix, a square pixel, its diagonal is actually square root in length, square root of 2 in length. If this is 1 and this is 1, so the diagonal, according to the Pythagorean theorem, is square root of 2. Does that make sense? And that's why I put square root of 2 here. We could have put 1. I mean, that's fine. It's just the model, and the accuracy of our solution is going to depend on how our model represents the actual reality. Okay.
Thank you.
Thanks, Anna. Okay, so the problem. Okay, so now the thing is, we cannot solve this by hand. I mean, we used to solve it by hand. Anybody seen like Hidden Figures, the movie? There were like computers,
Yes.
women computers. That's what it was. Pretty much, it was people that would, or mostly women actually, that would go and solve all of these like set of equations. But in order to do that, it's really hard. You have to do that in a systematic way. And if you have a computer that is actually a hardware that you could program, and you'll be able to solve. So we need to come up with an algorithm to solve this type of a set of equations that we can tell the computer, hey, you know what? How about you solve it? We don't want to do it by hand. We want to do it really quick. Okay, so we need to develop a systematic way how to do that. And so now we're going to talk about a very particular algorithm in order to solve these linear set equations. It's called Gaussian elimination. And in order to do that, we're going to have 3 basic operations that don't change the solution. And these 3 basic operations are multiplying an equation by a non-zero scalar. If we take an equation and we just multiply both sides by a non-zero scalar, we're not going to change the solution. Adding a scalar constant multiple of one equation to another equation will also not change the solution. Okay. And then swapping equations will also not change the solution. So let me show the third one. That's pretty easy, and I showed you last time. If I have a set of equation x plus y equals 2 and 3x plus 2y equals 5, if I swap them, they still will have exactly the same solution, right? Because, I mean, really, it doesn't matter if I call this a 1 or a 2, or I call this a 2 or a 1. It really doesn't matter from a solution point of view, right? So that is a trivial thing. So the proof is pretty obvious. I mean, that's, in this case, I can just say it's pretty obvious. Now, what about multiplying an equation with a non-zero scalar? I mean, does that apply? Is that really not changing the solution? The example that I have is, for example, if I have 2x plus 3y that equals 4, I'm going to argue that is going to have exactly the same solution as 4x plus 6y times 8, which is pretty much multiplying this by 2, this by 2, and this by 2. Okay, so I multiply both sides, and I'm going to argue that this has exactly the same solution. Okay, there is a proof that I am going to go over, but I'm just going to skip it right now because there's things I want to get to today, and I'm not sure I'll be able to get to that are important to. And so if bear with me and just believe me that this is true, there is a proof. The proof, we'll go over it. If we have time today, we'll go over it today, or we'll go over it on Tuesday. Okay, is that is that okay? I just want to waste. I just want to get to some other things, but right now, just believe me that this is true. We're going to show you that this is true in a systematic way, and there's actually a nice proof that we're going to go over that shows that this is true. But I'm going to skip it at this moment. The other one is that adding a scalar constant multiple of one equation to another. In this particular case, we're going to talk about, again, the set of equation, x plus y equals 2, 3x plus 2y equals 5. And what I'm actually saying here is that, you know what? If I take equation 1 and I multiply by 3, and then I add it to equation 2, I add equation 2 to it, okay? So this is 3 times equation 1 plus 2 will result in, okay, what is 3 times x? It's 3x plus 3x will give me 6x, okay? 3 times y plus 2y will give me 5y. And then 3 times 2 is 6, plus 5 will give me 11, so 11. So the way I'm writing it is 3 times equation 1 plus 2 will give me this. So now I have, again, a set of two sets of linear equations. And I'm going to argue that by doing this, I have not changed the solution. The solution is exactly the same. Okay. And again, there is a way to prove it. And the way to prove it is very similar to the way we're going to prove the first argument. So again, I'm going to skip it. I'm just going to say that the concept of the proof is try to look at an explicit solution. So just look at some x0 and some y0 as solutions and try to show that if that is true here, then it's also true here. And then also show the reverse. And we're going to go over it again when we have time, either today or on Tuesday. Okay, so for now, believe me, this is true. So we have three things that we're going to leverage now, either swapping, multiplying by constant, or adding a multiplication of one equation to another in order to manipulate our equations so that they're simpler to solve. Okay, that's the idea. So let me talk about a very simple set of equations that it's easy to solve. And I call these, we call these upper diagonal systems, okay? So consider this set of equation, okay? So x minus y plus z, 2z equals 1, y minus z equals 2, and then z equals 1. I can go and write that into the augmented matrix form, and that should be pretty trivial, right? Like I'll do the first row. It will be, what will be the first element?
1.
That's right. And then?
-1.
-1.
-1. That's right. And then?
2.
2. And then?
1.
1.
Perfect. And I can fill them all. And I know that some of you may be trying to also copy all of these at the same time. The point is really not for you to do this. There's we're going to again publish the notes for the class. So you know, there's a lot of matrices to copy, so it's just going to take you more time. So in these type of situation, I really recommend for you to actually look at what we're doing, and then you'll have all the notes written and given to you. Okay, so basically, again, mapping these two, and the reason I say that these are triangular, upper triangular systems is because they look like a triangular, right? So everything from the diagonal and up are non-zero, and then everything below the diagonals are zero, okay? That means that here we have 3 variables, here we're gonna have only 2 variables, and here is only 1 variable, and the other variables have 0 coefficients. Now, the thing is, why this is easy to solve? Why is it easy to solve?
You already have.
You already know it.
Well, Z, do I know what Z is?
Yes, we do.
Yeah, Z is 1, right? So that's not a problem. Well, I know what Z is 1, so I can put Z here. Right now, you have Y minus 1 equal 2. Well, that's easy. Then you know that Y equal 3,
Yeah.
right? And then you can substitute 1 here and 3 here, and then this is really easily solved. Okay, so it's trivial to solve this type of set of equations. Okay, so that's great. By the way, this is called an upper. So this is the definition of an upper triangular matrix. Again, it's going to have actually upper diagonal doesn't have to have 1s on the diagonal, but we're gonna, it's very often that you would see 1 on the diagonal, but it doesn't have to be. And then anything else above it. This is also called row echelon form. Okay, it's just I'm throwing you here some jargon, but it's called also row echelon form. These are called pivots. Okay, so if you look at every row, you'll see that there is a leading number in front of the other one. So this is the pivot. It's the leading one in front. So before that, there's zeros. And then after that, there's non-zeros. And this is, again, the pivot for this row. So again, jargon. And then a more general row echelon form is in the notes. Look at the notes for this more general row echelon form. It's a little bit more general than just upper triangular matrix. Upper triangular matrix is row echelon form, but there's other matrices that are also row echelon. So look at the notes for that. Okay. So now what we're going to do is we're going to go through an algorithm that would take a augmented matrix and turn it through these 3 operations that we said don't change the solution from a full matrix into an upper triangular one somehow. And this is called Gaussian elimination because we will eliminate variables. Okay. Now here's our set of equations: x minus y plus 2z equals 1, 2x plus y plus z equals 8, minus 4 plus 5y equals 7. I can go ahead and write that into the matrix. So it's going to be 1, minus 1, 2, and 1. And then it's going to be, help me here.
2, 1, 1, 8.
2, 1, 1, 8. And then?
-4,
-4,
5,
5, 7.
Oh, I love this. I love this. 0 and 7. I love this. Thank you for helping. Okay, perfect. So this is a full matrix, right? It's like hard to see the solution. What we're going to do now is we're going to try, we have to make this, turn this into an upper diagonal matrix. And the idea there is to perform a set of operations that would eventually eliminate the value here. That will be 0, and here will be 0, and then this one will be 0, and that will be easy to solve. Does that make sense? So we're going to start from trying to eliminate. Woohoo! Oh, sorry about that. I apologize. I know you're young and you have like good ears. For me, it doesn't matter. Apologize. I'll try to reduce the volume next time. All right. So that's what we're gonna do. Okay, that's what we're gonna do. And okay, so this was step one, just putting into this augmented matrix. Okay, so now in step two, I mean, this is fine, right? Like the top one is fine, right? Like we said, it's an upper triangle, so the top one is fine. I'm just gonna copy it. Okay, now I want to eliminate the variable here. I just want to get rid of it. I want to make its coefficient 0. Okay, so what do I do? Well, how do I make it 0? Well, I can take equation 2 and subtract equation 1 from it. Was that going to work? No, because this is one coefficient, right? But I need to eliminate this. So I'm going to multiply equation 1 by 2 and then subtract it from 2. Okay, so I'm going to do this. 2 minus 2 times equation 1. Okay, so multiply this by 2 and subtract from that. All right, and so what will be then the result? Well, the result is going to be, well, 2 minus 2 times 1 will give me 0. Oh, that's nice. That's what I wanted. 1 minus 2 times minus 1 is
3.
3. Okay. So again, this minus 2 times that. Okay, that's equals 3. And then 1 minus 2 times 2 equals minus 3. And then 8 minus 2 times 1 equals
6.
6. And I hope I had the right solution here. Okay, that sounds good. And then I want to do that again for the second row, for the third row. Again, I want to eliminate this minus 4. In order to eliminate this minus 4, I need to take 3 plus 4 times 1, right? If I take this one plus 4 times the first one, that's going to eliminate the left variables. Okay, so obviously this is going to be 0. And then what is 4 times 5 plus 4 times minus 1?
1.
1. And then 0 plus 4 times 2?
8.
8. And 7 plus 4 times 1?
11.
11, right? Okay, I got it right. Okay. So I got this, and now these variables are now eliminated. Okay, well, that's getting close to an upper triangular matrix, right?
Close.
Now, remember that these represent x1, these represent x2, and this represent x3 coefficients, right? And these are the b's, right? And so again, x1, x2, and x3, remember that, okay? So effectively now, I have equations here that don't have x1. Here it doesn't have x1. All right. Okay, let's move on. Now, I have this. I have 3, minus 3, and 6. You know what? I don't like this 3. It's on the diagonal. It's much easier if it's a 1. So what operation I can do in order to make it into a 1?
Scalar multiplication.
Scalar multiplication by what?
1/3.
Third.
By 1
Third.
over 3, right? So I can divide by 3. So I'm going to take equation 2, and I'm going to divide by 3. And the result is going to be 0, 1, 1, 2. Okay. And what about the last equation? Well, I don't need to
Professor,
do
I
any.
think it's -1.
Oh yeah, -1. Thank you.
Third column.
Mickey,
And yeah,
in the chat, several questions about, do we want to eliminate some elements and make the diagonal 1? Does the diagonal need to be 1? Does Do the pivots need to be 1?
Yeah, it's much
A
easier
bit
if it's 1.
confusion there.
Okay, so yes, we want to make it an upper diagonal, and we also want the diagonal to be 1 because it's much easier than to solve, and you'll see it later why it's easier to solve. Okay, once it's a 1, then the substitution do not require any divisions after that. Okay, so yes, we want to eliminate, make it into the upper diagonal and with 1s on the diagonal. Okay, so in that case, now it's good. You know, I have got a 1 over here, so 1 and a 1 and the rest. And what about the last one? Well, that's pretty good. It's already eliminated, right? This is eliminated and nice, and so I'm just going to copy it. Okay, so I just copied it. Okay, I copied this row over here. So now I have this situation, and now for this situation, I need to eliminate what? Well, this I don't care anymore. This is good. And now I want to eliminate this one. How do I eliminate this one? Well, again, I'm going to copy this to here. I'm going to copy this to here. And now I need to eliminate this one. Well, in order to eliminate this one, I can actually take this row and subtract it from this row. Sorry, subtract this row from this one. Okay, so 3 minus 2. Okay, 3 minus 2 will give me 0, right? Because 0 minus 0, 0 minus 0 is 0. And then 1 minus 1 is 0. 8 minus 1 is
9.
9. Oh, 9. And then 11 minus 2?
9.
9.
It's a 9. All right. Okay, well, that's great. Perfect. Now, again, this is a 9, so I want to make it into a 1 such that it's upper diagonal, and also 1 on the diagonal. Well, all I have to do is take row 3 and divide by 9. And when I do that, I get this beautiful form. So I did all these steps in a very disciplined way. First, I kept the first row, and if it wasn't, what if the first row was not 1 in the beginning? What do I do? The first step?
Multiply
Swap.
by 1 over the number that is now 1.
Just scale it by a scalar and make it 1. What if the first row actually had a 0 over here?
Swap it with
Swap the
another row.
rows.
Right, and then I would have swapped the rows. Right, perfect, very good. And so in a disciplined way, I first eliminated these first variables, right? So they were gone. Then this was not a 1, so I scaled it. And now I need to eliminate this 0, so I eliminate it. Now this was not 1, so I scaled it. This is a very disciplined set of steps. Eliminate, scale, if you need, swap, and then keep on going and eliminate the next variables. Okay, there's many ways that you can do it, by the way, in terms of like deciding which one to subtract, but that's okay. All right. So then we got to this point. That's great. Again, these are called pivots. Remember, these are the ones that lead the rows before them at 0. These are called pivots. Okay. All right. Now, I could have now go and do the substitutions, right? But that requires me again to do some operations. Right? I could say x3 equals 1, right? x3 equals 1, and then I can substitute it and then do all that stuff. But look at this. This is nice. What can I actually make that into a diagonal matrix without with zeros over here? If I have a diagonal matrix with complete zeros over here, then I would have a perfect solution. So is it possible to keep on processing now from the bottom and up such that we eliminate all the off-diagonal elements? Now, this process is called back substitution. And we're going to apply that from the bottom now and up in order to make this matrix a diagonal with ones on the diagonal, such that we immediately get the solution. If it's ones on the diagonal, that will be the solution. So how are we going to do that? Well, again, that's simple. The last row is perfect, right? Basically, it says that x3 equals 1. That's what it says. Okay, what about this? Can we eliminate now? Now we're going to eliminate from the right to the left, right? Before we eliminate left to right, now we're going to eliminate right to left. Okay, so can we eliminate this sucker? How do we eliminate it?
Absolutely.
That's right.
Since we have it in row echelon, we can turn it into a reduced row echelon by adding.
Okay, you're a little bit advanced here in the jargon, but that's okay. I like people reading ahead and also knowing the material ahead of time. But let's just try to remove this. How do I remove it? What operation do I need to do?
Let's add row 2
Addition.
with row 3.
Right. Let's
row
add
two,
these
row
two.
3.
Right. If we add these two, then this will be gone. Right. But because this is 0, it's not going to affect. Right. It's not going to eliminate this one. Right. That's the nice thing about doing it backwards. Okay. So effectively, I just copied this one, and then I'm going to do 2 plus 3. 2 plus 3 will effectively give me, let's say, 0 plus 0 would be 0. 0 plus 1 will be 1. And then 1 plus minus 1 will give me, check this out, a 0. Oh my God. And then a 1 plus 2 would equal a 3. That's beautiful. And what about the next? Well, I want to eliminate this one. So what do I need to do? Is I want to take the first equation and subtract twice the third equation. Okay. First equation and subtract twice this. And when I do that, I will get a 1, a minus 1, and then 2 minus 2 times 1 will be a 0. And then in this case, 2 minus 2 to that will be a minus 1. Okay. Any questions up to here? Are we good? We're just subtracting rows and eliminating. Now all of these are eliminated. Now we're just missing this one. We want to eliminate that one, and then we have the solution. Folks, already we know the solution for x2 is 3, right? Okay. All right. So now the last step would, again, copy this one, and we're going to eliminate this one. And this is easy to eliminate. All we have to do is take 1 plus 2. So this equation plus this equation will eliminate that. And when I do that, I get 1, 0, 0, and then 2. Okay, so remember, first we eliminate from the left to the right and created a diagonal matrix, an upper triangular matrix. And then we eliminate from right to left, from the bottom up, and we created a diagonal matrix. Now that's beautiful. This is called a diagonal, or actually an identity matrix. And it's also called a reduced echelon form, although a reduced echelon form is more general than this, and we'll talk a little bit briefly about that, but that's another name for that. And so now I got myself the solution. Effectively, z equals 1, y equals 3, and then x equals 2. Okay, that's is the solution. So in a disciplined way, we're able to solve this set of equations. Does that make sense? Okay.
There were several questions about, oh, is this the only way? Could we have done different things? Could we start from the other end?
Yeah, so there's all of this. No, well, okay, the answer is depends, but that will be a different algorithm. Okay, if you start at the another end or you do some other thing, that will be some other, or you can call it Jimmy's algorithm. And it might not be as efficient as Gauss elimination. And what we're trying to do here is Gauss elimination, because you can actually program in a computer in a disciplined way. You tell the computer, just do those steps, and the computer will do it, and you'll get the solution. You're guaranteed to get, well, you're guaranteed to get something. We'll get to that, what is the solution or not, but you're gonna get something, okay? And this is implemented, for example, in NumPy, or which is part of Python, and it's using what's called a LU decomposition, which decomposes matrices into upper and lower triangular matrices that will provide you the solution. So this is really implemented and used all the time, okay, for solving a large set. I'm not talking about 3 by 3. We're talking about 1 million by 1 million. Why not solving 1 million by 1 million, right? That's not a problem. Okay. Let's go back.
There were several questions also saying, what if the matrix is not squared?
Oh, yeah. So actually, the same steps should apply when the matrix is not square. We're going to actually touch this case in a sec, like in a few minutes. Okay. So let's just bear with me and let's talk about a few cases. And let's just go back to tomography, because it was a really, I love tomography. So it's the closest thing to MRI that I can think of, but it's much more simple in a certain way. Okay, so we have this. Remember that we first, when we did this tomography, we said, oh, we measure this and we measure this, measure this, measure this. 4 equations for unknown, right? They should be 4 equations show unknown. This should be a solution, right? We said that, and then it says, there was no solution. And I was like, well, I didn't show you that there's no solution. Well, let's actually look in a disciplined way what happens when there is necessarily, well, I guess in this case, there might be infinite. Well, we'll see. We'll see what happens. Let's just work with that. So here's the 4 equations, and we map them into the augmented matrix form. And now we're going to apply the Gaussian elimination to this process. We would like to eliminate and make this thing diagonal and find the solution and see what happens. You ready?
Yes.
Okay, we're gonna do it again. We're gonna do it again, folks. You're gonna see it over and over like 4 times today, 3 times today. Okay, so this is the matrix. Okay, this is the matrix. And yeah. All right, so now what we need to do is we have this. This is a 1, 1, 0, so that's okay. We can just copy it, right? Okay. And then the second one, that's already a 0, which is a good thing, right? That we want the 0 over there. It's already eliminated. So we're just going to copy that one too. Okay. And and all we look at is the first column. I don't care about what's the rest. I'm just going to look at the first column first. Okay. First column first. So here it's okay. Here it's okay. What about this? We want to eliminate that. In order to eliminate that one, what we're going to do is we're going to take 3 and subtract 1 from it. Okay. If we take 3 and subtract 1, what we get is 0, a -1, a 1, a 0, and a -2. Okay. Again, taking this row and subtracting this one from subtracting this one from it. And I can do, and then what about the last one? Well, the last one already has a 0, so I just copied it. Okay. All right. So now, again, I'm taking this one and I'm copying it here.
Question, Miki, from
Yes.
the chat. Could have you swapped row 4 and 3?
I could have done a lot of stuff, but again, in a disciplined way, we're just going to look at the first column. Yes, you can kind of optimize because you see it, but again, algorithm, like a computer, you'll then need to say, oh, wait, the second row has 2 0. It's like, well, it's complicated. Why? Let's just look at if you just need to make a program, make the program simple. Let's look at the first column, right? You're talking to a computer. You're not talking like it's a dumb computer, right? The computer just does what the computer does, right? It doesn't think. It thinks what we tell it to think. Even AI systems, we train them to do certain things, except that we just don't know what we tell them. That's the issue. All right, let's do that. Okay, so now we're going to look at the second column, right? But so this one is fine. Now we're going to look at here, and it says, look, this is a 0, but it's supposed to be a 1, right? So what we're going to do is we're going to swap, right? We're going to swap two equations such that there's a something here. And just to make it easy, you could actually swap, this one and swap it up, and then we'll have to divide and so on and so forth. I just wanted to make a shortcut, so I swapped this one, okay? But in a disciplined way, you would swap this one, okay? Because that's easier. Or you swap the first one that's non-zero, okay? All right, so I'm going to swap 4 and 2. And swapping 4 and 2 will then give me 0, 1, 0, 1. That's equation 4. It's swapped. And then this one is, I'm just swapping this. And so I would just copy this one and then, and then the swap. Okay, so all I did here is just swapped. Okay, one step. All right. So now I'm in a situation where I would like, so this is all good. Now I need to eliminate this -1. Okay, so I'm going to copy it here, and I'm going to copy the second row, and now I need to somehow eliminate. And how do I eliminate? Well, I'm going to take row 3 and add it to row 2, row 3 and row 2, and that would pretty much eliminate it. And so in that case, I would get a 0, a 0, a 1, and a 0 and a 3. Okay, add this plus that. Okay, and copy the last row, because the last row actually has already a 0. I don't need to eliminate it. So this is what I get. Hold on. Now I need to eliminate this one. But what happened? Look, here I get 1, 1, 3. Here I get 1, 1, 3. If I try to eliminate this one, what it also eliminates? It also eliminates this one. Okay, so effectively, if I try to eliminate this, I take 4 minus 3. This is what I get. I get a whole zeros. So pretty much, I don't have an equation. I mean, obviously, if x1 plus times 0 plus x2 plus 0, it's obviously 0. It doesn't matter what x1 is or x2 is. It's always going to be 0 if their coefficients are 0, right? So that means I actually have 3 effective equations because one of the equations had exactly the same amount of information. And so there's really infinite number of solutions in this case. I can pretty much substitute anything that I want into x4 and find a solution that satisfies that. Okay, x4 could be anything that I want. Okay, so once you get a 0 over here at the bottom, I got 3 equations, 4 unknowns, then they're going to be an infinite number of solutions. And that came from the Gaussian elimination. Okay, so, it either leads you to a case where that happened. Yes, Aman.
What if you have a situation where you start out with 5 equations and 3 unknowns, but you don't know how many of those equations are redundant? So how would you process that with the matrix?
We'll do that.
Okay.
We'll do that, exactly. But you don't actually, last time we did a back substitution, right, to solve for the equation. Sometimes it's actually useful to do back substitution over here because it tells you more information about which of the variables are completely free and which one actually are restricted, okay? And so we're gonna do that. We're gonna do back substitution, and so we have this, and we pretty much wanna eliminate this one over here, Okay, how do we do that? We can't. Okay, the only one that we can actually eliminate is this one. Okay, this one we cannot eliminate because we have a 1 here, but this one we can eliminate by subtracting, taking 1 minus 2. And if we do that, we get this. And now this is the solution that we have. And there's a nice structure to it. Okay, if you remember, this is a structure of what we called row echelon. And this is actually the actual row echelon, where you can also have a 0 over here, for example. And above the 0, you'll have, a lot of stars. And every time above a pivot, you'll have all these, whatever value that could be. Okay, and these are the pivots. So this is the definition of really a row echelon form. If you have a 0 over here, they can have anything above it. Okay, and then this is what's called a reduced echelon form, and it looks like this. And if you have a 1 on the diagonal, then above it, it's always 0. But if you have a 0 on the diagonal, then above it, there can be a value. Okay, that is a reduced echelon form. These are, again, called the pivots. But the nice thing about looking at this, these are called basic variables because they are on the diagonal, they have 1, and these are variables that are independent. And then you'll have a free variable, which is the last one, which you can just substitute whatever you want into it, and that would define the solution for the basic variables. Okay, and that's why you have infinite number of solutions, because the free variable can basically be anything. And once you decide what the free variable is, then it will define what the value of the basic variables. Okay, that's why we have infinite number of solutions. All right.
Mickey.
Yeah.
Question. What does this mean to tomography?
Well, it means that for this case, we didn't have a solution. There's many solutions, so we can't really solve the problem. The problem is called ill-conditioned or ill-posed, or in fact, underdetermined. That's another way of saying this. There could be many things, and we would not be able to reconstruct a good image. Okay, so that's why we need the X-ray equation, right? The diagonal one. Otherwise, we don't have enough to solve, right? We have uncertainty. In other situations, by the way, it could be useful. For example, if you're trying to optimize a path of a car and where you're going to press the gas and stuff like that. If you have degrees of freedom, maybe you can optimize energy, you can optimize speed, you can optimize, because you have a lot of solutions, so you can find the solution that fits you with that. So in some situations, it's a good thing. In this situation, it's a bad thing. Okay, so that's okay. So here's a different case that I want to also. What if instead of measuring 3 here, we measured 3.1? Can that happen? No? Of course it can. This is real life. We have a sensor. Sensor, has noise, all that kind of stuff. There might be an error in the system, and we measure 3.1 instead of 3. Right, that could happen. Why not? I mean, obviously, this is real life. It's a small perturbation. Okay, well, then the only difference in what previously have done is that we have a 3.1 here and a 0.1 here. I just emphasize the difference from the previous situation, okay? So we can go forward pretty quickly because it's the same solution, so we don't have to go over it again. I'm just going to point out where the difference is going to be. Okay, so how do we solve that one? Well, step 1, we have this with a 0.1. Step 2, we do exactly the same thing, but we have a 0.1 over here. Step 3, we do exactly the same here, but we do the swap, we have a 0.1 over here. And then we do this elimination, we have a 0.1 over here. Now that's where things are getting interesting. Because before, when we tried to eliminate this one, then we got a 0, 0, 0, which was, it's fine, it's okay. But let's now try to eliminate this case. Let's try to eliminate this case, and what would we get? Well, if I do 4 minus 3, oh, actually, sorry. If I do 4 minus 3, I get a 0.1. So you know what this says actually? It says the 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 equals to 0.1. Obviously, not good, right? Obviously not good. So what does it mean about solutions for these set of equations? There is some inconsistency here. These equations are inconsistent. And in fact, there is no solution whatsoever. We cannot find a consistent solution. Okay, so what Gaussian elimination told us through this process is that there is no solution, which is a good thing to know.
It's a result.
Yeah, it's a result. By the way,
There is
later
a
in the
question,
class,
Mickey.
Yep.
Go ahead, Yujun.
Yes,
Hi,
Yujun.
Mickey. So the previous problem, I was wondering, because you said that for the second row, and the last one couldn't be eliminated, but the second one from the first row could be eliminated. I just was wondering why is that?
Well, I'm trying to eliminate this one, right? And what I do is I take this and subtract from that, and then I get 0, 0. But then, when I subtract 3.1 from 3, I get a 0.1.
Yeah, the second row. You said that the last one from the second row couldn't be eliminated.
Which one?
From the second row.
This?
The last one.
I'm not sure what you're talking about. I'm sorry.
Yeah, this one. Yeah, the last one from the second row.
This?
From the second row, the last one from the second row.
Well, okay. And in the other case, well, I mean, how can I eliminate? If I eliminate that, then add, it will add over here, right? So it's like it will just move it around. Like if I subtract this from here, it'll just move the one around. So it'll move to here. So, it doesn't really matter. Like there's going to be always something value here. That's what I mean. That's what I mean.
I see. Okay, no problem. Thank you.
Okay, so there's no solution here.
Mickey, you have more hints.
I know. How about you ask those in the chat, because I really want to get to talking a little bit about vectors. And if you have questions about, clarification and things like this, please ask them in the chat. We'll try to answer you all this, but I think for the sake of brevity of time and 713 students waiting, I prefer to move on because there's a few things I want to discuss.
Go.
Looks like Frank is really. You can't ask it in the chat, Frank. Okay, all right.
I lowered his.
All right, so then here's again the situation where we have five equations. Okay, now we have 5 equations but 4 unknowns. What do we do? Well, we do Gaussian elimination, folks. It's the same thing. We want to reduce it to a diagonal. And obviously with 5 equations, we can either get a case where you have an inconsistent solution or a 0 at the bottom, because we're going to end up with 4 equations that are non-zero, right? That's what we're going to end up with. Okay, so I'm going to go very quickly here into the steps, because the steps are exactly the same as we did before. We're going to start eliminating things and moving things around. So first, we're going to eliminate the first column below this 1. And the way we're going to do it is, 3 minus 1 here and 5 minus square root of 2 times 1. And so we eliminate this. Okay. And then now we want to eliminate this, but we need to swap. Okay, so I'm going to do a swap. And in addition to the swap, I also did a scaling. So what I get is, 1's here. So again, it's a swap and scale. And now I want to eliminate these. So these are the operations that I'm going to do. And eliminated. Now I need to eliminate these two. And when I eliminate these two, basically I just need to eliminate the bottom one. So it's 5 minus 3, and this is eliminated. And now I have a case where 2, 2, 4, 4, because when you have 5 equations, 4 unknowns, obviously one of them is redundant. And I get, if I subtract this from this and I try to eliminate, then I would get a 0. And then of course I also scaled this to be 1. So it's going to be 1 and 2 here. So this is 1 and 2. Okay, so now I've got myself a nice upper diagonal that I can go and back substitute. And back substitute is eliminate this guy, and then eliminate in this one, and then eliminating all the rest of them. And the steps are 2 plus 4, 3 plus 4. Again, these were eliminated. That's already eliminated. Now I need to eliminate just this one. And when I do that, it's 1 minus 2. And now I got a beautiful diagonal. And I got a great solution. X4 equals 2, X3 equals 1, X2 equals 3, and X1 equals 1. Solved. Okay. And when I do that, then I can actually put and create an image. 1, 3, brighter. 2, a little bit darker, and then 1, darker, right? So now I got an image, which is pretty much a blurred version of this thing. And if you'd solve it for 256 by 256 variables, you would actually get this image, which is pretty amazing. Okay, let's do a geometric interpretation of what's actually going on over here. In the case where you have x plus 4y equals 6, 2x minus y equals 3. What does it mean? Well, there is a geometric interpretation. This actually defines a line. And this defines a line. So we can try and draw these lines on a grid. And how would we do that? Well, let's find the intercepts. Let's substitute x with 0. And if you substitute x with 0, then y would equal 6 over 4, which is 1.5. Okay, so that is one intercept point, and that intercept point is at x equals 0, 1.5, so it's over here. Okay, that's an intercept point. And then I'm going to put y equals 0 and compute what is x. And if I put y equals 0, I get x equals 6, because if this is 0, then x equals 6. And so now the other intercept point is 1, 2, 3, 4, 5, 6 over here. Okay. And now I'm going to draw a line between these two. Look at this straight line.
Amazing.
Amazing. And I can do the same for the second equation, right? So I can compute the intercepts, which is 0 and it's minus 3. And then the other intercept is 0 and 1.5. And I can draw a line between these two, and I would get this line. So that means my solution is where both of these intersect. And that is a single solution because two lines intersect at a single point. Two straight lines intersect only in a single point. And the solution is x equal 2 and y equal 1. And that is a possibility to solve, but only for 2. 3, try to draw a 3 graph, 3-dimensional graph, and it's like hard. So, but that's a nice geometrical interpretation of why you have a single solution for this case. Now, what about the case where there's infinite solutions? So let's look at these set of equations. The first one is exactly the same. The second one is 2x plus 8y equals 12. Let's look at the intercept point. Well, when x equals 0, y equals 1.5, right? X equals 0, then 12 divided by 8 is 1.5. When y equals 0, then 2x equals 12, so x equals 6. Well, it turns out it has exactly the same intercept point, and hence it's going to have exactly the same line. That means that this is exactly the same set of equation. It doesn't really give me more information. And my solution can lie anywhere on the line. And since it lies anywhere on the line, then I have infinite solutions because I can pick anything, and that will be true. Anywhere would be true along a line. And that's why it's infinite. Now, what about, so anything that satisfies pretty much x equals 6 minus 4 y0, some y0 would be a solution for this set of equations. So y0 would be the free variable, and then x will be the basic variable in this case. Okay, what if I change now, again, the second equation, and now it's 2x plus 8y equals 8. Okay, what would happen here? Well, the intercept point is x equals 0, y equal 1. And another intercept point is y equals 0, x equals 4. And when I draw that, this is what I get. And so where is the intersect point of two parallel lines?
Nowhere.
Never. By
Infinity.
definition, by definition, they don't intersect. Hence, no solutions. Okay, so this is the geometric interpretation, but it could be in an nth dimensional space. All right. Cool. So let's just summarize. First of all, in the notes, you have a full algorithm of the Gauss elimination. It's written in what's called pseudocode. It's not a specific programming language, but it just describes enough so that you can go and translate it into any programming language. And you can just go and look at this, and really this is the procedure. The first procedure makes it into an upper or row echelon form, and the second one is reduced row echelon form. Okay, and then you get a solution. So Gaussian elimination summary, we reduce the row echelon form from left to right using these three properties. And you either get a situation where you get something like this, where you would have a single solution, or you get something like this, which is an infinite set of solutions. And again, note that in this particular case, this variable was defined. So this is a basic variable. It's actually independent of the rest. It could be, but then these two, this pretty much is the free variable, and those depend on it. Okay, that could be a situation, and that's an infinite solution. And this is the case when there is no solution. You have some value over here, and you have zeros, and that cannot be. Okay, so in this case, you stop. You cannot continue because there's no point in continuing because it's just not defined. There's no solution, so stop. But in the other cases, you can go and back substitute to reduce row echelon from right to left, and you'll get, in a single solution, you'll get diagonal matrix, and in the infinite solution, you get a reduced row echelon form. So above the the diagonal of the free variable, you'll have these two whatever numbers. Okay. So this is kind of a summary of the Gaussian elimination. These are called pivots. These are called basic variables. And this is called a free variable. Okay. If you have a 0 and above it something, these are basically, this row represent the free variable. Yes, Christian.
Would that be a pivot, the one on row 3, or no for the infinite solution?
On row here there's no, I guess, what do you mean here?
Okay. Well, something about row 3, is that one at the very end to consider the pivot?
This is also a pivot, yeah, that's right, because there's 0,
Okay.
0, 0, and then a 1. Yeah, absolutely.
Okay, thank you.
Okay, so what I want to talk about now is vectors. Why? Because we want to examine you on this, and you're going to have enough exercise to do that, but we have pretty much 10 minutes kind of to go over it, so we cannot, we'll not go deep. We just want to give you a kind of idea of what are vectors and how they work. And probably a lot of you have seen this before, so it's not really new to you, but we're still going to assume that it's new. So pretty much a vector is just an array of n numbers that represent some coordinates in some, for example, in an n-dimensional space. So for example, the way to write it is that you have x vector, you're going to have this vector sign to it, and it's going to have elements in the vector, and usually, typo, it's going to be x1 and x2 all the way to xn. Okay. So we also say that X is in Rn. This symbol here represents in Rn, which means the space of real numbers, n real numbers. That's what this represents. Basically, it's the same thing as that, but in a fancy way. And for example, this is a two-dimensional vector in R2. And since it's in R2, we can actually display its coordinate and show you what it is because it's simple. And pretty much what it says that x1 is 3 and x2 is 2. So let's define this axis to be x1 and this axis to be x2. And so I should have a point somewhere by 2 by 3, which is pointing over here. Actually, a 3, but it's pointing over here. This is 3, this is 2. All right. So this is the vector. That's where it is, the coordinate. It's great. But they can also represent something, right? This is just the array of numbers, but it can represent other things. For example, I don't know if you have this thing, you know, on your laptop. If you're using Windows, it maybe look this different. But there's the sliders of red, green, and blue that you can create different colors, right? And I can actually create this color by a combination of red, green, and blue. So this is a vector representing this color. How much red, how much green, how much blue. Okay, that will give me the value of a pixel. Obviously, I can also represent an image using a vector. For example, if I had that image before of that piece of meat, and let's say it was a 2 by 2 image, x1, x2, x3, x4, I can actually represent them, those values, whatever those values were, as a vector. Now, somebody may ask, like, why shouldn't you represent an image as a matrix? If we want to do operations, we usually want to do operations on vectors, and we'll see later. But I just asked this question for you. Okay, but that's this is a representation of an image. You just need to know that it's an image, and you know, if you want to display it, you need to reformat it and like tell the screen to present it in a particular way. It can also be some data. It can also be data. Aman, just go ahead and ask in the chat because I just want to. We got 5 minutes, and I really want to get to a point. Sorry about that. And again, I'm really sorry I'm rushing, but I think it's okay. So data, I mean, this is, for example, the number of sunspots for a solar cycle since 1900, right? But I can take all these numbers and put them in a vector. X1 represent, you know, number of sunspots in 1900, and then X120 represent in 2020. Okay. All right, great. There are special vectors. There's the 0 vector, which are all zeros. There's the 1 vector, which is all ones. And there's also the natural vectors, or what we call E1, E2, and E all the way to En. And based on whatever number here is all the elements are 0 except 1. And those really represent the axes. If you think of, you know, a vector in R2, a 1, 0 would be the x-axis. A 0, 1 would be the y-axis. So these represent the axes. Okay, so these are very special vectors, natural vectors, basis vectors. What are matrices? Well, matrices, we've kind of seen them before, but pretty much I would argue they're just collection of numbers again, but now in a rectangular form. And they're numbered in this particular way. The first row will have the first element. So the first row would have the first element 1. And then you enumerate the second element, the second index, not element. And then second row, again, the first index would be 2, and then you enumerate the second one all the way to M. And it doesn't have to be rectangular. And then you go all the way down. And this would be then represented by capital X. These are small. And that would be R of N by M. Okay, so the reals, but structured in an N by M. But it's also a collection of vectors, because I can pretty much call this X1, and I can call this X2, and I can call this XM, right? Because if you think about it, it's x1, x2, like we did before with vectors. So it could be also a collection of vectors where pretty much each of these rows, this I call x1 vector, and this I call x2 vector, and so on and so forth. Vectors are pretty much degenerate matrices, because if I actually look at what a vector is, this is also R n by 1, right? It could be a matrix, but it's just one on one side. A scalar is actually also a vector of a matrix, but it's just be 1 by 1. Okay, so there's just the degenerate form of each other. Okay. Now, how do you add two vectors? Well, two vectors can only be added if they have the same length. If they don't have the same length, it's this. Like, it doesn't work. Okay, so these are two vectors, 3 and 2, minus 2 and 1. Sorry. Okay, I'll just reduce the volume on the recording next time. So what if I want to do x plus y? What does it mean? Well, I can draw x. This is x. And I can draw y. But then what I'm going to do is I'm going to start y from the end of x. And just going to plot it this way. And so x plus y would be x plus y. And the result would be this vector. And I can also write it down, 3 and 2 minus 1 and minus 2 and 1. And then basically I add this element to this one, I add this element to this one. So these add, and I'll get 1, 3, which is this one. What if I swap them? What would happen if I swap them? Same thing, right? If I swap them, I first put y over here, and then I overlay x on top of it. So here's x, this is what happens. And then you see it's the same result. And of course, it comes down if I have, I just flip the order. It doesn't really matter because they're just being added. And so I still get 1 and 3. So vectors really have this properties of commutativity. So I can, if I have addition, I can flip them. It doesn't really matter what order I add them. So if I add x and y first, and then I add z, or I add y and z first, and then I add x, they should be the same. If I add the negative, then I would get a 0 vector. And if I add a 0 vector, then I get the same vector. It doesn't change. Okay. Now what happens when you multiply a vector? Well, if I multiply, take a scalar and I multiply by x, then it just scales all its elements. That means that if I have, for example, this vector 3 and 2, and I scale by 2, I get 6 and 4. And it doesn't change the direction of the vector, it just changes the length. And so that's what would happen. What about another operation? This is an interesting operation. A transpose, a vector transpose. If I have x, which is r n by 1, and I apply a transpose to it, it will turn into a row vector. This is a column vector, and it will turn into a row vector. And the row vector will be of size 1 by n. It's kind of like a matrix, but with 1 on the first side. Okay. Now we're always going to assume that if you write a vector, it will always be a column vector. If you want to represent a column vector, if you want to represent a row vector, you have to transpose it. That will be, you cannot say x is a row vector. No, x, always a column vector. If you want to make a row vector, you need to transpose it. So I'm going to steal 3 minutes. I just want to go over multiplication. Okay. So I've learned in algebra class back in my undergrad, when you want to multiply two vectors, you have to do it like this and like that. What does that mean? There's only certain dimension where the multiplication is valid. and those needs to match. So if I look at a vector, it has to be this size and then this size. Those sizes needs to match, like this and like that, okay? What does that mean? Is that if I have a column vector of length n and a row vector of length n, I can multiply these together because they have the same size, like this and like that. What about, so these have the same size. What about this? Is that going to work? Well, I can actually take the first element, cross section here, that's fine. And then I cross here, that's fine. They have, again, the same sizes, so that's okay. So these are the two options that I'm able to do. All right. So in order to do that, if I have two vectors of size Rn, I can multiply them together by taking y transpose times x. In that case, y transpose will have y1, y2, all the way to yn, and then I'll have x1, x2, all the way to xn. And then the way I'm going to multiply is, again, like this and like that. I'm going to take this element and multiply by this element, which will result in y1 times x1. But then, hold on, it's like this and like that. I haven't finished. I'm going to take the second element and I'm going to multiply by the second element and add that to the first. y2 and nx2. And then I'm going to take the third element and do the same and add them all together. At the end, I'm going to take yn and xn and then yn and add them together. So the result of this would be a scalar, 1 by 1. Okay, so this is the result. y1 multiplied by x1, y2 by x2, and so on and so forth. And that's going to be a scalar. And this is actually known, it's what's called an inner product, okay, or a dot product. And it's just 1 by 1. How do we know it's 1 by 1? Well, that's what happens. What about multiplying over here? Well, multiplying over here, I will have x1, x2, all the way to xn. And then I'll have y1 all the way to yn. And now I'm going to do like this and like that. Okay, so like this, I'm going to take x1 and like that, multiply by y1. And that's x1, y1. And that's going to be the element. That's it. Because it's only whatever is covered by my hand. Only this element is covered by this element. And then I'm going to take like this and like that and move to the second element in y. And so I'm going to take x1 and then y2. And then the second element is x1 and y2. And then so on and so forth. So if pretty much in this case, I'm going to get a matrix if I keep on going like that. And this is going to be the result. So the result is actually an n by n of this operation. You're going to go over this also in the, and this effectively means that I cannot commute these two. If I commute these two, then they result in a different solution. Okay, and this is also called an outer product. So there's things that you are allowed to do and things that you're not allowed to do. And according to what we covered then, is you need to have some matching dimensions. So we said some dimensions are good and some dimensions are not. And that's along the, like this and like that. So what if you multiply x and y? Don't fit. All right, don't fit. What about this case? X and y here. Do they fit? Yeah, they fit. And the result is going to be 1 by 1. Okay. And what about this and this?
No.
No, because they're not the same size. Like this, like that. Not going to fit. And what about that? Yes, this is a 1 by 1. So that fits, right? So those dimension fits. In this case, I'm going to get an n by n matrix. And what about this and this? That should also be good, but then because this is a M and this is an N, I'm gonna get a M by N matrix. All right, I rushed through it, but I'm gonna do it again. We're gonna go over it more slowly next time. And with that, I would wish you a very nice what day
Labor.
do we have? Labor Day. Yeah, sorry about that.
Thank you. Bye.
Thank you.
Thank you,
Thank you.
Professor.
Thank you.
Sorry for stealing your
Thank
time.
you.
Thank you.
Thanks.
All right, thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.